Welcome back. In the last part of this lecture, we introduced two very important things. We introduced the Krieger-Doherty relationship, a very good general purpose model that can describe the relative viscosity over a very wide range of particle volume fractions. We also examined how the maximum particle volume fraction is affected by how particles pack together, which is a very important concept that we can use to explain phenomena such as shear thinning. In this part of Lecture 15, we're going to introduce two competitive mechanisms, one that causes disorder, Brownian motion, and one that causes order, shear, and that order and disorder we're going to see affect the maximum packing fraction, hence the viscosity response of a suspension. We will see that the result we introduce is only applies to very, very small diameter particles, so it only is for colloidal suspensions. We will also see quite nicely that the shape dependency of this result falls to zero. So the result that we'll look at for colloids is valid for any particle shape. So here on the board in front of you is a cartoon of spherical particles in hexagonal close packing. Maximum packing fraction 0.74. Now, if these particles are really small, say a few hundred nanometers in diameter, then thermal effects such as Brownian motion will cause disorder, and the random nature of that will affect the maximum packing fraction. If we go from this ordered system of hexagonal close packing, one can perhaps see that if we add random fluctuations due to thermal effects into this that move the particles about, maybe an accurate descriptor of the maximum packing fraction is actually random close packing, which has got a significantly lower maximum volume fraction, 0.64. Now, if that is our disordering, let's think about ordering. Let's go from random close packing and apply something to the system that causes ordering. Now, we know that shear forces can cause particle translation and particle rotation, and the presence of shear forces on a suspension actually increases the amount of order in that system. So it might transition, for example, a randomly close-packed system into a hexagonally close-packed system, increasing that maximum packing fraction. So let's concentrate on this ordering to start with. Let's remind ourselves of the Krieger-Doherty result. So there on the board is the Krieger-Doherty result. And remember that one of the important terms is that ratio phi over phi max, the volume fraction divided by the maximum volume fraction. Now let's assume for the instant that the volume fraction of particles remain constant. Shearing, however, will affect the maximum volume fraction. And so if we transition from random close packing to hexagonal close packing, then we can see that phi max will increase between those two scenarios. Phi over phi max decreases, and hence the relative viscosity decreases. So the application of shear causes the relative viscosity to drop, which is exactly what we see in shear thinning systems. Now, if we imagine Brownian forces, then introduce disorder into that system, over time we can see a viscosity recovery. And if you remember what we were talking about in the lecture on thixotropy, then we can see that this competition between Brownian disordering and shear ordering not only describes shear thinning, but actually a thixotropic response as well. Now, here is an equation called the Williamson equation. We're not going to go into the derivation of this, but this includes ordering effects and disordering effects. Now, that term in blue on the right-hand side in the denominator is the critical stress. Let's examine this term a second. The critical stress is derived from a Peclet number. It's a balance of shear and thermal forces. So it's a balance between that ordering and disordering mechanism that we were talking about. If we look at the Williamson equation and look at the terms on the left-hand side, we can see that that is in effect a viscosity ratio. It's the same form of viscosity ratio that we used in the Carrier-Yasuda equation all that time ago when we were talking about generalized Newtonian fluids. And so we can see that that viscosity ratio depends on an expression that involves the shear stress over the critical shear stress, And so if we think that the shear stress in a system is imposed by shear, the critical shear stress, therefore, is going to be as a result of Brownian motion. And we can see whether or not, for a given particle radius, we get these shear thinning nathixotropic effects that we've been discussing. If we examine the expression for critical stress a little more closely, we can see that there's that term Kb in the numerator, the Boltzmann constant. Key thing about the Boltzmann constant, it's a very small number. And in the denominator, we have an r cubed term. So if we imagine that ratio Kb over r cubed, if that's to be order 1, r has to be very small, hence the applicability only to colloidal systems. T is included in the critical stress as well, because the higher the temperature, the higher the amount of thermal force present. However, it's only a linear relationship with T. Now, if we think about that expression for critical stress, there's no shape dependency in here. It only depends on radius and temperature. And we can see that the critical stress at 25 degrees C is going to be of order 10 to the minus 21 over r cubed. So, take home message, this is for very small particles. Now, let's plot out some of the results for this theory. So here on the board is viscosity from the Williamson equation as a function of shear stress in Pascal. Now, the numerical parameters I've inserted into the Williamson equation are there on the board. Eta 0 is 1 Pascal second, eta infinity, the high shear rate plateau, is 0.1 Pascal second, so a decade decrease in viscosity. The temperature is 25 degrees C, that affects the critical stress. And there's a power law in that critical stress ratio, which for the time being I'm just setting to 1. So, if I choose my particle radius to be 100 nanometers, we can see that there is that full decade of viscosity decrease over roughly 3 to 4 decades of stress. So the curve that we get looks a little bit like a Caro-Yasuda fluid. We've got that low viscosity Newtonian plateau, the high viscosity Newtonian plateau, and a shear thinning response in between the two. Now, if we were to increase our particle radius to 1 micron, we see that actually the lowest viscosity in the system has reduced to roughly 0.5, 0.6 Pascal second. And the shear thinning occurs over a far lower range of applied shear stress. If we increase our particle diameter 1 order of magnitude more to 10 microns, we barely see any shear thinning, and the viscosity is that of the high shear rate plateau. So, here is an underpinning that the Williamson equation is only valid for colloidal systems, systems where the particle diameter is very, very small. Now, let's just have a quick look at how P, that power law, affects the shape of these viscosity curves. So here's that shape for 100 nanometer radius particles for P equals 1. If we change P to 2, we get this dotted response. So it sharpens that shear thinning, and the shear thinning region occurs over a far smaller range of shear stress. If we decrease P, there's the chain dotted line now, P corresponding to 0.5, we widen the shear thinning range. So P is a useful parameter that we can use to tune the viscosity response of the model to match experimental data. Now, there is another important and relevant phenomenon that we haven't got time to cover in full, which is that of shear thickening, the reverse of shear thinning that we've been talking about for so long now. There are certain suspensions, and you've seen in the introduction to this section on rheology, one of these suspensions, cornflour and water, where over a range of shear rates, fairly low range of shear rates, you get shear thinning behaviour. So there on the board, the first part of this plot is shear thinning. However, as shear increases, something rather remarkable happens, and you get shear thickening happening at high shear rates. Now, there are many competitive theories to describe why this might happen. One is called hydroclustering, that high shear rates drive out the fluid between particles, and particles aggregate together, forming larger radius entities that increase the viscosity. There is another theory, however, that suggests that what is actually happening is that roughness on the particle surface, asperities, cause friction between particles at high shear rate. At high shear rate, particles come into contact with each other far more regularly, and so these friction forces start to dominate the system. And at increasingly higher shear rates, those interparticle frictional forces contribute to a rise of viscosity. We're going to leave shear thickening there. It's an effect that you should be aware of. It's an effect that is documented in the literature should you need to examine it in more detail. So, let's recap a few key points. For colloids, Brownian motion can cause our maximum packing fraction, phi max, to decrease because Brownian motion induces disorder in a system. Shear forces will cause phi max to increase regardless of whether you've got a colloidal system or not. The Williamson equation looks at this competition between disorder and order and presents a result that can describe shear thinning in colloidal suspensions. We saw the range of particle radii, diameters, that this equation applies to, and we saw that below about 1 micron radius the effect is very pronounced. We've mentioned very briefly in passing another phenomenon, shear thickening. It's something you need to be aware of, but we're not going to be exploring in any detail here.